Okay, so as you can see by the whiteboard, test Monday. Don't forget. Um, Take it online. There's going to be no class, so your only job Monday is to take the test. In case you missed it, it'll be open from 8 a.m. to 11:59 p.m. It should be an hour. Should be how long I give you to take the exam. So you just need to find an hour throughout your day where you can sit and focus and take the exam. I'll send out like an official breakdown. Probably it's not going to come out till tonight or like Saturday, but we'll see. Somewhere in that general ballpark. Okay, so we need to finish up aromatic compounds, right? So we went over kind of basic aromatic compounds, things that just have carbons in the ring, right? There's a few other things we have to be able to do, right? So now we can talk about aromatic ions. So compounds that have a charge, right? So a positive charge on a carbon, plus you, gives you 0 electrons towards your electron count. But gives you 1 p orbital. So the carbon that has a positive charge on it has a p orbital, but because all a carbocation is an empty p orbital, it gives you no electrons to your electron count. So a negative charge gives you 2 electrons plus 1 p orbital. So if you have a carbanion, you're getting a p orbital that your electrons can move through, and there are 2 electrons in that orbital, so it's giving you 2 electrons to your count. So if you have, so this is kind of the stock example for carbocation. Right, we're just going to say this is a flat ring. So does every carbon have a p orbital? So these carbons here are all part of a double bond. So yes, they have p orbitals. And then the carbon that has a positive charge, that positive charge is giving that carbon a p orbital, so it also has a p orbital. So you end up having p orbitals all the way around. So you've met the p orbital requirement. And then how many electrons do we have in this ring of p orbitals? We have 6 total. We have 2, 4, 6. The carbocation is just giving us a p orbital for those electrons to move through, but isn't giving us any electrons. So this is going to be 6 electrons. So this is going to be aromatic. For a carbanion, this is kind of a go-to example. Again, this is a flat ring. Does everything have a p orbital? These atoms there are all part of a double bond, so they count as having a p orbital. And then our carbanion, that has a p orbital, right? There has to be an orbital for those electrons to be hanging out in. So that gets the p orbital, so everything has a p orbital. And then how many electrons do we have? We get 2 from here, 2 from here, and then 2 from the carbanion. So there are 6 total. Reasonable? So is my top left compound aromatic, non-aromatic, or anti-aromatic? It is anti-aromatic. So it's a flat ring, because again, that's the gimme. P orbitals, right? We've got all of our P orbitals around our ring. We got our carbocation. So we all have P orbitals, so we're good there. Check, check. And then I have 8 electrons total. 8 electrons is a 4n number of electrons, so this compound is anti-aromatic. Oops. What about our top right structure here? How many electrons does it have? 2 electrons. So everything has a p orbital, right? Is 2 a 4n plus 2 number of electrons? Yes, when n is 0, that equals 2. So this is a 4n plus 2 number of electrons. So this is aromatic. What about bottom left?
Someone asked if having a carbocation decreased the number of electrons.
It doesn't affect it. So the positive charge just gives you a p orbital and no electrons. So you can just think of like the carbon that has a positive charge just has an orbital those electrons can move through, but it's not adding any electrons to the count and it's not taking any electrons away. It's just an open door for them to run through. Bottom left. Non-aromatic, right? We failed the second criteria. Not everything has a p orbital. We have p orbitals on the double bonds, p orbitals for the anion, and then a big womp womp. No p orbitals there. So this is non-aromatic. Right? And you don't have to list any electrons or anything, right? Because when we're listing the number of electrons, we're listing the number of electrons in the unbroken p orbital chain. And if you don't have a p orbital on every carbon, you don't have an unbroken p orbital chain. So you don't have to list electrons. So for non-aromatic stuff, you'll never have a number of electrons associated with it. Easy enough. Aromatic compounds can be heterocycles. Heterocycle is just a fancy way of saying rings that contain atoms other than carbon. So we're going to be concerned with like 3 heteroatoms. Do we have to learn the rules for how you count their electrons? Right? So we're concerned about oxygen, nitrogen, and boron. I regret not doing it nitrogen, oxygen, boron, because then it would be knob, but I'm full of regret now. Here we go. We'll fix it. Knob. All right, so we're going to start with oxygen now, because oxygen is like the easiest, or like to see everything with. So let's start with oxygen. Oxygen is going to give you 1 p orbital plus 2 electrons. Right? So our kind of go-to aromatic compound that contains oxygen is furan. Right? Oxygen has 2 lone pairs. We only count one of the 2 oxygen lone pairs. Great, so we count this. And we don't count the other one. I'll tell you why in a second. I'm not just going to like leave you hanging. All right. So if we look at this compound, every atom has a p orbital, right? Because the carbons are part of a double bond. The oxygen has that lone pair that we're getting to count like a p orbital. So you can think of a lone pair as kind of like a carbanion, right? It's the same kind of thing. It's an orbital that has 2 electrons in it, right? So this ends up being, again, flat. Everything has p orbitals, and it has 6 electrons. So it's aromatic. Right? So why do I only count one of the 2 lone pairs of furan? Right? So let's look at what furan looks like if we tip it on its side. So I'm going to do the same thing to furan that I did to benzene before. I'm going to kind of look at it on its side. Right, I got my p orbitals that make up my double bonds right there, right? And now for the oxygen, one of the lone pairs, its orbital is up and lines up with the other p orbitals from the double bonds, right? So these all line up so the electrons can move through them. The other p orbital is roughly here, around 90 degrees from all the other orbitals. If you remember, if electrons are at 90 degrees from each other, they don't know the other ones exist. Like basically every girl in me from like, the age of 14 to like 22, right? So it's cold-blooded, right? I played a lot of Final Fantasy. All right, so these orbitals are the ones we're not counting. Those electrons don't count because they're perpendicular to all the other orbitals. And so those orbitals that are making the double bond don't know those 2 electrons even exist. Right? So you only have to get to count one of the lone pairs because only one of them is interacting with the p orbitals. So now I'm not going to draw the lone pairs on an oxygen, right? You have to remember that oxygens have lone pairs and you need to count them. So like if I gave you, let's say, this is a little ugly, I'm sorry. It's a lot ugly. Let me try again. I feel bad. I feel bad for it. Right? Is that compound aromatic, anti-aromatic, or non-aromatic? This is going to be anti-aromatic. Again, we're going to assume it's flat. We have p orbitals from all of our double bonds. And then we get our one lone pair that gives us a p orbital on our oxygen. So we're good there. And then this is going to be 2, 4, 6, 8 electrons. And so it's going to be anti-aromatic. Yeah, we'll wait. So we go with oxygen. Seems pretty straightforward. Then we have nitrogen. Nitrogen, less straightforward. So there are 3 types of nitrogens that we have to worry about. 3, 4. I don't know. There's a lot. In grad school, the general rule of thumb was that for each nitrogen in your molecule that you had to make, you just had to add a year to your PhD. All right. So the first type of nitrogen is easy, right? So nitrogen with 3 single bonds, right? It's going to give you 1 p orbital and 2 electrons. All right. So if your nitrogen has 3 single bonds, easy money. Right? So it's basically just like an oxygen, right? But it only has the one orbital. So these all line up. So then 3 types, question mark. Right? So this is 6 electrons and this is aromatic. Right? Because we're counting the one lone pair from our nitrogen. It lines up with all the other orbitals. Easy. If you have a nitrogen that has 4 single bonds, right, and a positive charge, you have no p orbital. So right, so this is different than a carbon with a positive charge, right? So there's no p orbital on this. Even though it has a positive charge, there's no p orbital. So you break the second rule of having to have a p orbital on everything. So flat, yes. P orbital, no. So this is non-aromatic. Right? So you might be wondering, like, why does a carbon with a positive charge give me a p orbital, and a nitrogen with a positive charge doesn't give me a p orbital? What's different? So for a carbon, right, you've taken electrons away and you've left this empty p orbital. For a nitrogen, the way the nitrogen made itself positive is, right, those lone pairs that lone pair that we used just a second ago to count to be aromatic, those electrons went and became part of a bond. So that orbital that was on the nitrogen that we could move through, it now used its electrons. We're going to make this magical positively charged methyl thing, not a real thing, right? It magically gave those electrons to a carbon. So now you've got a bond in that orbital. So there's just no empty orbitals, no free orbitals. Nitrogen's using all 4 of its orbitals to make bonds, and so it can't move electrons through it, right? So nitrogen's positive because it's given away too many electrons. Carbon became positive because it had an empty orbital, right? Nitrogen's making too many bonds, full up, can't do anything else. Carbon just had an empty orbital. So it's a little bit different on how you got to the positive charge. Right, so that's nitrogen with single bonds. Cool. Now let's talk about nitrogen with double bonds. If your nitrogen has a double bond, it's giving you a p orbital from being part of a double bond, but it's not giving you any electrons. Right, the nitrogen itself, you're not counting its lone pair. So, right, if you look at this nitrogen has a lone pair. We don't count that lone pair. So even though that nitrogen has a lone pair, we don't count it this time. When nitrogen's on a double bond, you don't count its lone pair. All right, so this is flat. Everything has a p orbital, right? So the carbons are part of double bonds, so they have p orbitals. And to be part of a double bond, the nitrogen has to have a p orbital. So that double bond makes sure that the nitrogen has a p orbital. So we're good on p orbitals. Right? Total number of electrons, 2, 4, 6 electrons. We're not counting the lone pair. So why don't we count the lone pair? Same reason we didn't count that one lone pair on oxygen is when we draw this structure out. Right, my bad, nitrogen here. Well, here, let me get rid of my, oops. Let me actually draw the orbitals, sorry. Right, so I've got my orbitals that make my double bonds, right? They're all lined up, perpendicular to the plane of the ring. And then this lone pair that we're not counting is perpendicular to all those orbitals, right? So they don't see those 2 electrons there, so they don't get the count. So when you have a nitrogen that has a double bond, it almost just acts like it's a carbon on a double bond, right? Its lone pair doesn't matter. You're just saying, hey, you give me a p orbital and we're good. Fun fact, that nitrogen-containing molecule is called pyridine. It smells really awful. But apparently, back in the 40s, 50s, and 60s, male chemists believed that if you did a shot of pyridine, it would render you temporarily sterile. So they'd be like, yeah, I'm going out on the town. I'm going to do some shots of pyridine before I go out, you know, just in case. I think one, they call those people parents, or I guess at this point, grandparents, right? And 2, like, that was like never a concern. Like, I'll tell you, like at the bar, so what do? I'm a chemist. That's got to go. My friends are looking for me. like like that wasn't like, oh, you're a chemist. Oh, come on, let's go back to your place. I was like, oh, you're a doctor? What kind of doctor? Oh, one that doesn't make money. I gotta go. I gotta. You drive a Ford Escort? Ooh, this is taking a turn. Uh, all right. So then, okay, we definitely more than there's definitely four now. Nitrogen with a double bond and a positive charge. If you have a nitrogen that has a double bond and a positive charge, that positive charge doesn't matter. It doesn't have an impact on anything. It's basically just like if it didn't have a positive charge. So if you have this, right, that positive charge doesn't matter. This is still going to have it's still going to be flat. Everything's going to have p orbitals. So we're good here and here. And it's still going to be 6 electrons, so it's still aromatic. Right? Where did the positive charge come from? We use those two lone pair electrons that we didn't count before to make a bond. They didn't matter before, so we don't care that they wouldn't made a bond. Right? We didn't count them before, we don't have to worry about them now. Right? So we basically, I'm going to go back a slide, took these two electrons right here and just said, like, you want to make a bond? Cool, don't care. Right? So having a positive charge on your nitrogen doesn't matter. I guess there's one more because there's 5 types. So this is 2 single bonds and a negative charge. So this is 1p orbital plus 2 electrons. So basically it's oxygen. So let's say we have that, right? For nitrogen to have a negative charge, it has 2 lone pairs, right? It has the one that you're drawing as a negative charge, and then it's got a lone pair. We only count one of those 2 lone pairs, just like it was an oxygen. So this ends up with, we'll say, hey, we're not going to count these, bonk, bonk. Be 6 electrons in aromatic.
The question was just kind of about like my titling of the top of the slide, like how the first 2 lines ran together.
Yeah, so maybe we should do this. Whoop. So nitrogen with a negative charge, you're looking at a nitrogen that has 2 single bonds and a negative charge on the nitrogen. So, armed with all of this knowledge now, so top left, aromatic, non-aromatic, anti-aromatic. It's aromatic. How many electrons are there? 6 electrons. Right, so we have p orbitals here, 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 and on the nitrogen from the double bond. Right, we get a p orbital on this oxygen from the lone pair that we're counting. So we're good on p orbitals. And then we have 2, 4, and then the lone pair makes 6 electrons. What about top right? This one's also aromatic. How many electrons does it have? 10. So again, all of our double bonds are giving us p orbitals. Then we have, again, the p orbital from our lone pair on our oxygen. We have 2, 4, 6, 8. Lone pair on oxygen makes 10. Bottom left. Bottom left is actually aromatic. So this is, everything has a p orbital, right? Here, 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 and here. So we're good on p orbitals, so it's flat, has p orbitals. And I've got 2, 4, and then lone pair on nitrogen makes 6. So that's 6 electrons again. So aromatic. Yeah, so I get 2 here from this double bond, 2 from this double bond, and then 2 from that nitrogen. Like counting the lone pair on the nitrogen. And then the last one, anti-aromatic, anti-aromatic, right? And it's going to be 8 electrons. So 2, 4, 6, lone pair on nitrogen makes 8. So the way these are set up on the exam right now is I give you like 4, and then there's just a pull down menu with a mixture of like aromatic 6 electrons, anti-aromatic 8 electrons, aromatic 10 electrons. And so you have to match it being aromatic, anti-aromatic, or non-aromatic to the right compound, and then pick the one that also has the right number of electrons for it. So I couldn't do this one where I have 2 that are aromatic 6 electrons. Right, so you would, so at least that gives you something. All right.
The question was if I was going to draw the lone pairs on nitrogens or if just like oxygen, I wasn't going to put them in and you just had to know that they were there.
I'm not going to draw them, no. Nitrogen, I'm not going to draw the lone pairs either, yeah. So you're just going to have to look at a nitrogen and go like, it has a lone pair.
So the question was oxygen has 2 lone pairs and we only count the one.
Exactly. Oxygen has 2, you only count 1. So like when I'm drawing in the lone pair, I'm only drawing in the one that we're counting when we're doing the count, but it has 2. All right, top left, aromatic. Didn't mean to cut you off, Zoom. Right, so here, 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 and then on the oxygen, all our p orbitals, and we have 2, 4, the two lone pair. The lone pair we can count on oxygen makes 6. The carbocation is just giving us a p orbital, no electrons. Top right. This next one's anti-aromatic, right? So we have, right, everything has a p orbital, the nitrogen, these parts of the double bond, and then the anion. We have 2, 4, 6, and then the lone pair on nitrogen makes 8. This is anti-aromatic and 8 electrons. Bottom left. This one's non-aromatic. Right, I don't have p orbitals all the way around. Right here, I don't have a p orbital. And then last one. This one should be aromatic. Should have 10 electrons. And then the lone pair on nitrogen right there. So then we're going to have 2, 4, 6, 8, 10 from counting the lone pair on nitrogen.
The question was, does the nitrogen in the compound on the bottom left have a lone pair?
Which one? Here? Yeah. So it has a lone pair, right? It has a lone pair right here, but this lone pair does not count. Right, because it's perpendicular to all the other orbitals, so we don't count that lone pair. So there's one more atom left that like your homework likes to throw in all the time, and that is the oddball of the periodic table, boron. Boron is basically, you can think of it like just like a carbocation, right? Boron always has an empty p orbital, right? It's the one atom in the first like 10 that doesn't make an octet. So boron is going to give you one p orbital, but 0 electrons. So basically, it's just like having a carbocation, but with more steps. So you're just like, all right, I have p orbitals because of my double bonds. I have a p orbital because of boron. My electrons can move through there. How many total electrons do I have? I have 4, right? 2, 4. I'm getting nothing from boron other than that p orbital. So this is 4 electrons. So it's anti-aromatic. And then what about the other one? It's aromatic. 6 electrons and it's aromatic. Right, I have p orbitals again from my double bonds. And then a p orbital from my boron, and I get 2, 4, 6 electrons. Seem good? So boron's super easy. You just, like, in your head, just be like, you're a carbocation. I know how to do a carbocation, so I know how to do boron. Right, C plus is really close to B. Yeah, great humor. Yay. All right. So there's one more thing to kind of talk about, and that is carbonyl groups, right? So that's C double bond O, right? So if you have a C double bond O on your ring, the easiest thing to do is to draw the resonance structure of that carbonyl and then determine the aromaticity. So I said words and, whatever. This is a picture class. So, right, let's say you have, let's think. We'll do it this way. So you have this, and it's like, oh, is this aromatic or not? Right? There's some different ways to think about it, but I think the easiest thing to do is if we draw the resonance structure where we just move the electrons up onto that oxygen, right? Get them out of the ring. But what is that going to do? That's going to give us a carbocation in the ring and some electrons up on the oxygen outside of the ring. Right, so now all you're doing is you're looking at this, right? And you're not worried about the negative charge on the oxygen. Right, so now is this ring in my orange box, is it aromatic or not? It's aromatic. Right, so I think it's just easier to like look at your carbonyl compound by just moving those electrons out, making the carbocation, and then doing it from there. It just makes it simpler to figure out. So if we have this, draw the resonance structure, right? We move those electrons out of the ring. Oops, I should make that something legible. Go out on a limb there. Right. So what would that be? Anti-aromatic. All right, so right there are all of our p orbitals, right? And then we have 2, 4, 6, 8 electrons. So what usually will happen is if moving your double bond, if drawing that resonance structure will lead to your compound being anti-aromatic, the molecule goes, no, I'm never going to make that resonance structure. So it will try to break the like having an unbroken chain of p orbitals, right? By not putting that positive charge on the carbon of the C double bond O. It'll just be like, nope, I'm not going to ever do that resonance structure. So I can exist, but never have to be anti-aromatic. So like this compound here, right? You can totally buy this compound, right? But if you were to have, but if it made its resonance structure, it would be anti-aromatic. So it's just like, I'm not going to make that resonance structure. Just envision Danny DeVito. No, no. And he's like, no, I'm not going to do that. No, thank you. I'm just going to hang out over here and not be anti-aromatic. So the compounds where you can move the electrons off the carbonyl, that's like an easy way to kind of do the aromaticity, but they don't always do it. And they kind of almost think of it as being a little bit less aromatic than if it was just like a benzene, right? Because there's some part of the time that their resonance structure isn't aromatic, right? When you're like this, right, when you try to move the electrons around, the electrons go out to the oxygen. They don't make it all the way around. So that's why you have to move the electrons out first, put that positive charge, and that lets them move all the way around. That's why you have to get rid of the double bond. Because when you push the electrons, they go out to the oxygen. You're like, well, no, I need to go back around. I have an answer.
The question was, do you guys have to worry about the kind of the corner case where it doesn't make the resonance structure?
Yes. But for us, right, for us, we're just going to say, like, if I say, like, hey, is this compound aromatic, anti-aromatic, or non-aromatic? You could just say this is anti-aromatic, right? But in reality, if this question existed on like the test, just tell me it's anti-aromatic. I won't make it sketchy. Yes. Yes. Don't worry about that. Just like I said, not to worry about like, oh, this molecule is gonna fold itself in a weird way. It's hard for you to predict that. So I'm just not gonna ask you to. All right, it's 9:50. I will see you guys on Wednesday. Please don't forget to take your test. That is my biggest fear, is that someone will forget to take their test.